Good morning and welcome to this next lecture on sound and structural vibration. So we have been looking at a case of sound radiation from a panel set in a baffle. A few things I'd like to mention, it's never too late. This is what we call uncoupled analysis. We have seen coupled analysis in case of the classical problem, the waveguide, okay, and the panel backed by a cavity, but this is uncoupled analysis or one-way coupled analysis. Okay. The other thing I want to mention is I use K for acoustic wave number. I could at times use Ka also. Similarly, I use lambda for the acoustic wavelength. And similarly, I could use lambda with a subscript A. Okay. Then for medium density, which is mostly air, okay, I use rho or rho 0. So the mean fluid density either. Okay, sometimes I use rho 0, sometimes rho. And similarly, so the fluid density, fluid mean density. And similarly, I use C or sometimes C0 for sound speed or sonic speed in the fluid. Okay, this is common. Now, what have we seen so far? We have seen a case of a rectangular panel, finite, placed in a rigid wall or baffle. Baffle extends to infinity in all directions. Okay, and we formulated the Rayleigh integral for pressure. Okay, then from there we made a far field approximation. In a closed form for closed form integration. Then we went to far field intensity. Okay, and we looked at maximum values, where maximum values occur. Okay, and condition for the maximum values, okay, which is K greater than P pi by A and K greater than Q pi by B. So here I would like to clarify one thought. Okay, when we spoke of coincidence frequency right in the beginning, okay, in the infinite 1D plate case, okay, then we had the fluid wave number and the plate wave number Kp or Kb, okay, and Kb is something like m omega square by d to the power of fourth. So this, and then we said coincidence is k equal to kb, and we also found the coincidence frequency. So it was equal to c square something something. Okay. Now this is the kb is the free wave number in the infinite medium. That means somewhere remotely far away there is a localized excitation given, and what now propagates in the medium is kb. Okay. And for this infinite medium, the coincidence condition is this. Okay. So k less than kb, it is absolutely no sound. Okay. And k greater than kb, suddenly sound. Yes, sound, the far field. Okay. So it's a 0-1 situation. This is the we'll call it the infinite panel coincidence. Okay. Infinite panel or plate coincidence. And there is only one wave number, and there is an infinite panel. In an infinite panel, at one frequency, at 1 omega, there is only one free plate wave number, kb. Okay. This changes for finite panel. Okay. The single modal wave number, So what did we do? For a 1D case, we said Vn of x comma t is equal to V tilde p sine p pi x by a and e to the power j omega t. So p pi by a is the modal wave number. Okay. And now because this is placed in a baffle, okay, so I know the velocity from 0 to a, and I know the velocity from a to infinity, which is 0, and I know minus infinity to 0, velocity again 0. So along this plane I know the velocity, and so Fourier transform can be taken. Okay. Because I know the velocity, Fourier transform can be taken. And that generates extra wave numbers. So this finite panel modal wave number, because it sits only in a finite region, it scatters. Okay, it scatters and generates extra wave numbers. Okay, whereas in an infinite panel there is no such scattering and only one wave number remains. Okay, so the coincidence now we speak of. Okay, so we found the Fourier spectrum for this Vn. Okay, excluding the time term, we found the Fourier transform of this, and it had a peak at p pi by a and again at minus p pi by a. And then the scattered wave numbers. Okay. So here we said when Vn happens at a certain omega, that omega translates to omega by c a certain k, and then we can draw the k line and integrate between them, and that generates sound. Okay. And as k grows or higher and higher omega is taken, we get more and more sound radiation from these scattered waves, and finally when k crosses p pi by. So this is another coincidence. Okay, this is coincidence with the modal wave number. This is not the coincidence in the infinite panel sense. So there are two coincidences one has to understand. Okay. So in the infinite panel case, infinite panel coincidence, below coincidence no sound, no sound below coincidence, below coincidence. In the finite panel, okay, some sound, there is some sound below finite panel coincidence. Okay. So finite, for finite panels we are looking at this coincidence. So please note that. Okay. Now let us see what is the full picture once again. Okay, the full picture. So we have a 2D plate, full regular 2D plate. And let me see, I have and we'll make it oblong this way. So this is the wave number space in 2 dimensions. Okay. So this is pi by a, this is twice pi by a, this is thrice pi by a, 4 pi by a, and so forth. And this is pi by b, this is 2 pi by b, this is 3 pi by b, 4 pi by b, and so forth. Okay. And these crossings are modes. These are modes of the plate. Okay. And so as the plate is vibrated at low frequencies, we start at low frequencies. Okay. Then we have our acoustic quarter circle. This is K, acoustic wave number circle. Okay. Now at low frequencies, the infinite panel wave number KB, okay, the infinite panel wave number is greater than the acoustic wave number. Okay. So this is the, let's say, blue line. This is the infinite panel wave number. Okay. Now we also know that kx square plus kz square is equal to kb square. In an infinite panel, remotely, if there is a excitation at a single frequency, you will get kb, and that relates to kx square and kz square, which are in some way unknown. Some boundary condition will decide what it is. But, and this is equal to m omega square by d 1/4. Okay. But we also know that p pi by a whole squared plus q pi by b whole squared is equal to omega pq, okay, m by d to the power, or yeah, to the power 4th and a root. Okay, we know this information also. Okay. So now let us see on this picture what happens. At low frequencies, KB happens to be higher than K, okay, and in general KB obeys this law, okay. However, when this KB line passes through these nodal points, KB line passes through these nodal points, then it obeys this law, which is those modes are in resonance. This is the equation for resonance, okay, of a mode. Okay, just check. So this is equal to KB. Sorry, my mistake here. So this is KB squared. Okay. So this is half, and therefore this is omega PQ, and this is also half. Okay, please note here. Okay, in any case, so when KB, this KB line passes through these nodal points, okay, then those modes are in resonance. But the K quarter circle is below, and so you will have initially modes in resonance, but not above coincidence. Above coincidence, okay, they are modal coincidence. This is, okay, mode related coincidence, this one, okay, not above modal coincidence. But what is happening? Just as in the 1D case here, because it's a finite panel, okay, and you have V tilde PQ sine P pi x by A and sine Q pi Z by B occurring on a finite dimension, okay. So you will have scattered wave numbers like this picture. So some of those scattered wave numbers will be radiating sound, okay. And if it's resonance, of course there will be some amplification and you get more sound. So in this range it's resonant radiation dominated, but modes are below coincidence, okay. So now let us say the K circle moves up a little here, the K circle, K quarter circle is over here, okay, and I draw the bounds of K. So this is K, this is K, this is K, this is K, okay. So now what happens is these modes their Q pi by B, okay, their Q pi by B values, which is this direction values, are below K. So in this range these are Z edge modes, okay, Z edge modes. Similarly here the P pi by A values are below this K value. So these are X edge modes, okay, and these here are corner modes, okay. Here both P pi by A and Q pi by B are greater than K, so they are corner modes. So in the beginning when K quarter circle is small, all the modes are corner, they begin with corner, and slowly based on the dimensions A and B, they either end up in X edge modes or Z edge modes, okay. Then there is a region here, okay, where square root of P pi by A square plus Q pi by B whole squared is greater than K, but K is greater than P pi by A and K is greater than Q pi by B, okay. So this region is double edge modes, XZ edge modes, okay. And finally modes enter the acoustic circle. These modes are within the acoustic circle, these become acoustically fast modes, okay. So now as frequency is raised at some instance, what you will have is that the K quarter circle and the KB line, the blue KB line, they coincide, okay. So when they coincide, those node points where this blue line crosses are resonant, and now they are just below their modal coincidence. So then you have both resonance and coincidence, okay. So you get from those modes the most efficient radiation, and then as further increase you will have the K quarter circle dominating, okay. We had drawn this picture somewhere in the beginning where acoustic wave number line is like this and KB line is like this. You have repeatedly seen it. So somewhere, this is now infinite panel coincidence. Okay, so beyond the infinite panel coincidence wave number or frequency, you will have the acoustic wave number above the infinite panel wave number. Okay, when that happens, just at that instance, those modes that this goes through or passes nearby the blue line are resonant and as well as just above coincidence. And beyond that, what happens is all these modes below the red line become coincident. I mean, they move above their respective coincidences, and some of them become resonant also. So you have some modes in their resonant and above coincidence radiation. So that's how the panel radiation picture looks like. Okay. Now there are a few important papers, important journal papers that have contributed to this understanding. One of the key ones is by one C.E. Wallace. Okay, and the paper title is radiation resistance of a rectangular panel. Okay, published in 1972 in the Journal of Acoustical Society of America. Volume is 51, part 3. Okay. So now in here, what he does, okay, is he discusses radiation resistance mode by mode, modal radiation resistance. What is that? We have radiation efficiency given by the actual power radiated by the panel divided by rho 0 Cs and mean square space time averaged velocity. Okay, so let me say a word about this once again. Okay, so let's say there are a few panels with this vibration pattern. There's a panel with this vibration pattern. There is another panel with, let's say, this vibration pattern, and there's a third panel with this vibration pattern. Just looking at 1D, suppose. Okay, then let us say that their vibrational power is same. Power is same. That means the mean square velocity is same. Mean square velocity is same. Okay. Now, sound is related. Sound is first of all generated from vibrations. And therefore, if we want sound power, okay, we talk of sound power. Hypothetically, it will be this vibrational power into some other terms which talk about sound radiation. Okay, mathematical expression that presents sound radiation. That means this carries the efficiency effect, how efficiently the radiator radiates. So it will be different for a different radiator. So it will be different now for this case, for this case, for this case, even though this term is common. Okay. And what is the efficiency effect? It's cancellation. Okay. Right now, how are we saying one radiator is more effective, one is less effective? It's because of cancellations occurring on that. So if sound power is known, that means this term is known as a composite. This term is known as a composite, not as these individual terms. We know the sound radiation. So dividing, there should be a square here. So dividing first of all by this takes out the common vibrational effect, common vibrational power effect, that is removed. All that remains is the radiation factor, how efficiently the source is radiating. Okay. So if we now have the radiation efficiency, it is obvious that it will be defined as this sound power, okay, which is this entire term divided mainly by this V tilde square and the vibrational power. Okay. So what should effectively remain is the other factor which discusses radiation. Of course, there are these terms placed in there for making this a power from a circular piston. Okay. So now radiation resistance is sigma rho 0 Cs. So that's equal to the sound power divided by mean square velocity. So that's what Wallace discusses in this paper modally, mode by mode. Okay. So now how do the curves look like? These curves, they look like this. These are radiation resistance curves. They start off and they reach with a value 1 somewhere, and at times they cross over also, and then asymptotically back down to 1. Okay. So let's say this is some mode 1 comma 1 mode, and this is 1 comma 2 mode, okay, and this is 1 comma 3 mode or 3 comma 1 mode, and so forth. Okay. Now at very low frequencies, very low frequencies, based on the cancellations, every mode, this can be 1 2, let's say this could be 3 comma 1, every mode, okay, starts off as we saw with a single cell at low frequencies, and the single cell dimension could be different based on the aspect ratio and mode number. Okay. So you can see that the 1 1 mode will have the biggest quarters at the 4 corners. Okay. So it starts off higher and cancellations within it are less, so it has the highest radiation efficiency or radiation resistance. Okay. Whereas all other modes with higher number of half circle patterns at low frequencies, the area of a single panel is much smaller, and therefore they radiate less sound, and so they start off from a lower value. Okay. And what is this non-dimensional frequency? is given the term gamma, and it is the acoustic wave number divided by the square root of p pi by a whole squared plus q pi by b whole squared, which is the modal wave number. Okay. So non-dimensionally this is gamma equal to 1, but dimensionally it is different because each mode has its own p and q. Okay. So this is not coincidence with kb, the infinite panel wave number, it's coincidence with the modal wave number. Okay. So each mode as it approaches its modal coincidence becomes efficient. Okay. So this is Wallace's work, and time has run out, so let me stop here. We'll continue next class. Thank you.